Hello and welcome to our fourth session of the short online course about the geology of Scotland. For those of you who joined this course later, it consists of 6 presentations, namely an introductory presentation followed by 5 others, each of which is dedicated to one of Scotland's terranes. As a quick reminder, each of the slices of continental crust that make up Scotland and are bounded by major faults represents a terrane. These terranes have a geological history of their own, and their age decreases from the northwest to the southeast. The present configuration of Scotland is relatively recent and was acquired only about 400 million years ago. The purpose of the course is to discuss the chronological formation and deposition of the major rock units in each of these terranes, and to have this accompanied by maps. We've had 3 sessions so far: the introduction, the Hebridean terrane, and the Northern Highlands terrane. This is our 4th session and is dedicated to the Central Highlands of Scotland, also known as the Grampian terrane. The Grampian terrane is the middle of the crustal fragments that make up Scotland, both in terms of geographical location and age of its oldest rocks. It is bordered by the Great Glen Fold to the northwest and the Highland Boundary Fold to the southeast. The oldest rocks are also known as the basement rocks. As we can see on this map, the largest outcrop occurs on the mainland, while a much smaller outcrop appears at the surface in 2 islands of the Inner Hebrides. These rocks are metamorphic, but do not represent a single continuous unit that outcrops in different locations. They are completely different rock units, with a unique history of formation and different ages. Let's start with a smaller outcrop, which is so small that if we didn't have a blank map and we weren't aware of it, we probably wouldn't even realize it's there. So let's zoom in to the islands of Islay and Colonsay. The basement rocks here are known as the Rins complex, which for long was believed to be part of the Lewisian complex of the Hebridean terrane, or at least it was believed to be very similar to it, much like the basement rocks of the Northern Highlands. But it turned out that wasn't the case. The Rins complex is not a relic of the oldest crust preserved on Earth, which dates back more than 2,500 million years, and it wasn't formed by the melting or recycling of such crust either. Instead, it represents younger crust, sometimes called juvenile crust, that formed more recently, about 1,800 million years ago. It was formed in a subduction area or a volcanic arc setting by the ascending of mafic magma. And it may represent a fragment of a more extensive belt of young crustal blocks that formed at the margin of older Archean cratons. Soon after formation, the rocks were metamorphosed and transformed into gneisses. We have here an instance of gneiss of the Rins complex from a small beach on the west coast of Islay. The other basement rocks in the Grampian terrane outcrop in the mainland. This is the Badenoch group, and was deposited as sediments in a shallow marine environment. The source of the sediments was at least in part an ancient mountain chain, the Greenlandian orogeny, that was eroded about 900 million years ago, so the sediments were deposited approximately in the same period. The rocks of the Badenoch group were metamorphosed during the Neodartian orogenic event, around 800 million years ago. If the Neodartian sounds familiar, it's because it's the same event that metamorphosed the rocks of the Moyne supergroup in the Northern Highlands that we discussed last week. During the Neodartian orogeny, the rocks of the Badenoch group were exposed to high temperatures and pressures and were transformed into gneisses. They also suffered partial melting and were severely deformed, so a special kind of rock resulted, and that is migmatite. This is a close-up view of a migmatite, a metamorphic rock that has been partially melted to the point it is not exactly a metamorphic rock anymore, but it's not quite an igneous rock either. It falls somewhere in between, and if we notice its texture, the gray areas of the rock represent the metamorphic part that was not affected by melting, while the orange and pink areas represent the part that was melted. We've seen that the basement rocks of the Grampian terrane are represented by two distinct units, and although both are made of gneisses, which are metamorphic, they have different parent rocks. Those of the rings complex formed from igneous rocks, while those of the Badenoch group formed from sedimentary rocks. Also, the Badenoch group contains migmatites, which are metamorphic rocks that were partially melted. The basement rocks also have different ages. The rings complex formed about 1800 million years ago. The Badenoch group more than 800 million years ago, although the oldest mineral grains contained are 1800 million years, indicating a recycling process and the source located as far away as Greenland and Labrador. Let's move on to the next chapter and talk about the rocks that were deposited on top of the basement rocks. These are sometimes referred to simply as the basement cover. They can be broadly divided into three categories: the Dalradian supergroup, that covers most of the mainland and the inner Hebrides, a rock succession assumed to be equivalent of the Dalradian supergroup in the Shetland Islands, and a local basement cover for the rings complex. Because we had a discussion of the Shetland Islands included in the previous session, we will not discuss it this time. Let's start again with the inner Hebrides. The 1800 million year old rings complex is covered locally by the metamorphic rocks of the Caledonian group. These were laid down as sediments that originated in part from the eroded underlying rings complex, but also from the erosion of the Granville orogeny and various other sources across Laurentia. The exact deposition interval is unknown, but believed to be younger than 900 million years. The sedimentary rocks were later metamorphosed under low-grade conditions and strongly deformed. On the mainland, above the basement rocks of the Badenoch group, is an impressive assemblage of rocks, the Dalradian supergroup. Within the Grampian terrane, they are as widespread as the Moyne supergroup is in the neighboring northern Highlands. They both represent rock successions that were deposited at the margin of the ancient continent of Laurentia. Their deposition, however, was separated in time by the Neodartian orogeny that occurred about 800 million years ago. The exact interval of time during which the Dalradian supergroup was deposited is still debatable, but believed to have happened between 800 to 500 million years ago. The rocks of the Dalradian supergroup are not as monotonous as the ones of the Moyne supergroup. The Dalradian supergroup was originally deposited as sediments into a series of rift basins associated with the Breakup of Rodinia. As continental masses were separating from each other, the continental crust was pulled apart. This created a series of basins that were gradually filled with sediments carried by rivers from the neighboring areas. As the surrounding landforms were eroded and more material was added, the load of sediments increased. Faults developed at the margins of the basins, and the basins began to sink in a process called basin subsidence. This process of faulting and sinking of basins repeated itself several times, allowing for large amounts of sediment to be accommodated. Also, every episode of subsidence was accompanied by marine transgressions. As the breakup of Rodinia continued and the continental masses were pulled apart, the continental crust containing these basins eventually broke, creating new oceanic crust. The remains of Rodinia assembled briefly into another supercontinent, Pannotia, that was very short-lived, probably the shortest lived of all supercontinents. And when Pannotia also broke up, a new ocean began to form. This was the Iapetus Ocean, the ancestor of the nowadays Atlantic. What makes the Dalradian supergroup special and very interesting is that this prolonged transition between the breakup of Rodinia and the formation of the Iapetus Ocean is recorded in its rocks. So next, let's have a quick look at the four groups of rocks that form the Dalradian supergroup. The first group to be deposited was the Grampian group. If you remember from our introductory section, group is a very general rank in the classification of rock units. So we're not going into details, we just want to understand how these groups reflect the changes from a continental to an oceanic environment. The Grampian group was deposited as a succession of coarse-grained and medium-grained sediments that alternated with each other. They were carried by rivers and laid down onto the continental shelf. Therefore, they record a fairly rapid transition in the deposition environment from fluvial to deltaic to shallow marine. Basin subsidence was occurring rapidly. In other words, the basin was deepening and sinking as a combined effect of the continental crust being stretched and thinned, and the load of sediments that were brought and deposited on it. The Apine group was the second to be deposited, and consisted of a rather drastic change in composition, from the generally more coarse-grained sediments characteristic of shallow waters, to progressively finer and finer sediments that were settling into deep waters. The presence of carbonate rocks indicates the formation of coastal lagoons that had little oxygen. The stretching of the continental crust intensified, and so did the sinking of the basin that was accompanied by transgressions, or episodes of sea level rises. The Apine was followed by the Argyle, which is probably the most interesting of the groups of the Dalradian, because of the variety of sediments that were deposited and the changes that they reflect. Around 700 million years ago, there was a period of severe glaciations that were so extensive the ice caps were not limited to the interior of the continents, but reached all the way to the continental margin. And this is reflected in the glacial deposits called tillite that contrast with the marine sediments. These tillites are made of rocks and fragments of rock that can vary in size from boulders to small pebbles. All of them were caught together into a fine matrix, which in time solidified. The marine sediments record a transition from stable to unstable conditions. Let's remember that sometime in this period, the supercontinent Pannotia also assembled and then broke up, and this occurred over a very short period of time. So the tectonics involved in the formation and destruction of Pannotia may also have affected the deposition environment of the Dalradian supergroup. Faults eventually developed at the edges of the basin, so the marginal slopes became unstable. The basin started deepening suddenly, and the sediments turned into a chaotic mixture called turbidites. And we can see in this image that turbidites, sometimes look like the solidified version of a landslide. And indeed, they form by strong underwater currents and landslides when the continental slope along which sediments are carried to the ocean floor becomes unstable. This may happen simply because there is an overload in sediments, or can be triggered. Around 600 million years ago, the continental crust eventually gave way. This was accompanied by massive magmatism, both in the shape of intrusions and lava flows. As the new ocean floor was created and more lava erupted, it came in contact with the cold seawater to form pillow lavas. The newly formed oceanic crust gradually opened to form an ocean. This was the Iapetus Ocean. Following its opening, the sediments of the Dalradian supergroup were increasingly turbiditic because of the still unstable conditions. Then the volcanic deposits became dominant and were represented by lavas, basalt lavas that were very hot and fluid, and also layers of volcanic ash. The Iapetus Ocean separated the continental masses of Laurentia, Baltica, and Gondwana. Now it's a bit improper to call Gondwana a supercontinent, because it didn't comprise all the existing continents, but it was definitely very large and consisted of the assemblage of most of the remaining landmasses except Laurentia and Baltica. The Iapetus Ocean lasted for about 200 million years, and its existence straddled the boundary between the Precambrian and the present Eon, the Phanerozoic. This time interval gave the Dalradian sediments enough time to consolidate into sedimentary rocks. The closure of the Iapetus Ocean around 500 million years ago generated a magnificent orogenic event, the Caledonian orogeny, which, similar to the other orogenies that preceded it, for example Granville, consisted of several individual orogenic events. The first was the Grampian event, which was caused after a volcanic arc terrane separated from Gondwana crossed the closing Iapetus Ocean from one side to the other and collided with the margin of Laurentia. The portion of the Laurentian margin where this volcanic arc collided was exactly the Grampian terrane. Despite being a direct collision, metamorphism was not very intense, so the physical and chemical composition of the rocks did not change drastically. Because of this, the rocks, although metamorphosed to a medium grade, retain much of their original sedimentary character. The deformation was very intense, however. The rocks were folded and rearranged, but even despite this, the overall geometry of the depositional basins remains relatively well preserved. The second metamorphic event was the Scandian, that was caused by the collision between Baltica and Laurentia. This wasn't the first collision between the two continents. They had collided before during the Granville orogeny. This time the Grampian terrane was a bit farther away from the collision point, so the Scandian orogeny had little effect on it. We've seen that the basement cover of the mainland and the inner Hebrides is made of metamorphic rocks. The Colonsea group covers the local basement rocks in some of the inner Hebrides. The Dalradian supergroup occupies most of the mainland. Both were deposited as sediments starting from about 900 to 800 million years ago and can be broadly correlated. The deposition of the Dalradian was longer and took place into a series of basins that witnessed the events between the breakup of the supercontinent Rodinia and the opening of the Iapetus Ocean, and this includes the formation and breakup of the supercontinent Pannotia. The deposition, however, was not continuous. The sedimentary rocks of both the Colonsea group and the Dalradian supergroup were metamorphosed and deformed during the Grampian event of the Caledonian orogeny, but retained much of their sedimentary character. If we have another look at this map, the striking thing about it are the many gaps that are spread throughout much of the mainland, which makes the map look like an incomplete puzzle. And indeed, some of the missing pieces represent igneous intrusions, or plutons. Some of you probably remember this image from our first meeting when we discussed plutonic rocks. These rocks form when magma rises from the Earth's upper mantle and intrudes the Earth's continental crust, where it cools down slowly and solidifies into a diversity of bodies. Plutonic rocks are the opposite of volcanic rocks, which form from magma erupted at the surface as lava. The Grampian terrain was affected by several episodes of magmatic intrusions. Different magmas originated at different depths. Those coming from shallower depths were rich in light elements, while those coming from greater depths were rich in heavy elements. The plutons formed from felsic magma were granites. Those formed from mafic magma were gabbros. We can see that these rocks differ in composition. The light-colored minerals in granite are made of light elements. The dark-colored minerals in the gabbro are made of heavy elements. The rocks are similar in texture, however. They both have grains that can be seen with the naked eye, which means that it took a long time for them to cool down. Most of the plutonic rocks of the Grampian terrain are associated with the opening and closure of the Iapetus Ocean. Of all, let's focus on the granitic plutons. They are the largest and most numerous, and can be broadly divided into the older granites that were emplaced during the opening of the Iapetus Ocean, and the newer granites that accompanied its closure. In the case of the older granites, the volume of magma was not particularly large, and the granites are relatively small. In the case of the newer granites, magma accumulated in huge volumes. Some granites were formed during the Grampian event, but the vast majority formed during the Scandian event. Those in place during the Grampian event were later deformed. During the closure of the Iapetus Ocean, magma that accumulated beneath the Grampian terrain was very hot and very buoyant because of the high gas content, and since it had no way of escaping, it uplifted the whole terrain a few kilometers in a process called epirogeny. Epirogeny is a term that can be easily confused with orogeny, which is a mountain building process. However, epirogeny does not involve the folding or folding of rocks, so no deformation occurs. In addition to the basement rocks and the basement cover, we've seen that a significant area of the Grampian mainland was intruded by plutonic rocks. In time, as the rocks of the Dalradian supergroup were gradually eroded, these plutons appeared at the surface. Their composition varies, but most of them are granitic, and their formation is linked with the existence of the Iapetus Ocean that separated the ancient continents of Laurentia, Baltica, and the rest of the continents that had assembled into Gondwana. The older granites formed with the opening of the Iapetus Ocean, and can also be referred to as pre-Caledonian granites. The newer granites formed during the closure of the Iapetus Ocean and are also sometimes referred to as Caledonian granites. And now, let's see very briefly what other rock units there are in the Grampian terrain. The Old Red Sandstone, a very interesting unit that we mentioned briefly last time, and we'll talk more about it next time. One thing to remember is that the Old Red Sandstone is incredibly widespread, not only in Scotland, but around the North Atlantic region, and this includes Scandinavia, Greenland, and Canada. In Scotland, it accumulated in three major basins, one of which was the Orcadian Basin, that was shared between the Northern Highlands and the Grampian terranes, and was located where the Moray Firth is now. And in the Grampian terrain, the Old Red Sandstone outcrops in other areas as well, for example in Argyll and along the Highland boundary fault. And now we can finally say that we've covered most of the rock units of the Grampian terrain, which is the third oldest terrain in Scotland. The basement rocks are represented by the Rings complex, which is the oldest, and the Badenoch group, which is the most extensive. The basement cover is overwhelmingly represented by the Dalradian supergroup that was moderately metamorphosed and severely deformed during the Caledonian orogeny. Among the plutonic rocks, which are also widespread, the most important are by far the newer granites that formed during and after the closure of the Iapetus Ocean. And finally, the last major rock unit deposited was the Old Red Sandstone, which represents material from the erosion of the Caledonian mountains that outcrops mostly around the Moray Firth. That was all for today. Thank you very much for joining me, and I hope it was an enjoyable experience for you. See you next week.
Well, good evening, everybody. I'm Don Stewart, a trustee of the Scottish Geology Trust and very active member of Aberdeen Geological Society. My location is just outside Aberdeen. I'm passionate about the whole Grampian terrain. Slight apologies, this presentation will show a few tasters with quite a strong leaning towards the northeast of Scotland, my home patch, but I do stray across to the southwest here and there. Basically, I've got just over 20 slides, and they are meant to be just tasters of landscape, rocks and minerals, a bit on glaciation and quaternary geology. It's a very, very varied area with all of these things covered. Apologies for any obvious omissions. It's just a quick collection to whet the appetite, I guess. So the introductory slide here, I was very lucky to be flying a little Cessna plane and able to take some nice pictures. And here is the Highland boundary fault from the air looking towards Stonehaven with a very, very conspicuous fault plane showing. I just happily got exactly the right angle. And you can see it crossing Craigieven Bay there. If I go to the next slide, you'll see the reverse view. So we're in Craigieven Bay looking back towards where I took the previous picture from. And again, the fault plane is very, very evident with all the dolomitic distorted pillow lavas close to the fault. And then further over, the deep black shales characteristic of the Highland boundary series, complete with jaspers and cherts in places. So this is the edge of the patch we're talking about just now. We're into Highland rocks on this side of the fault. So I just introduced the borderlands of the Grampian terrain here in Stonehaven. Following on now, I'm going to just dart around a little bit, just show some nice examples of bits and pieces. This is a little known sill in the cliffs just south of immediately south of Aberdeen, close to a feature called the Cave of Red Rocks. It's a magnificent sill, at least 5 meters thick in places. And this is the northern end where you can see the truncation of it. And we go there frequently and wave our arms about the formation of sills within the country rock, where you can see a fairly obvious stratification uninterrupted in this point, and yet you've got this huge lozenge of a sill inserted. So that's an interesting one to do a bit of arm waving in. I mean, these are all Southern Highland. We were just starting to talk about the Southern Highland series with Alex's talk. So these are all Southern Highland series Dalradian rocks. And this is a felsite sill. It's been of Caledonian origin at some point. Now I'll jump right across the country to, here we are on the edge of the Ben Nevis caldera. If you walk over Einach Moor and then drop down to the Bialach or the col at the back to Einach Beg, you look back and you see this magnificent formation, which is the caldera edge next to the Dalradian Leven schists. So this is a quartz diorite, a outer member of the caldera. And here is the boundary to the country rock, the schists round about. Very, very impressive, very visible. We're looking through the gap there to the Great Glen. So you're looking sort of northwestwards. This is a well-known, another succession, the Glencoe. I've just borrowed this slide. But again, what I'm trying to show here is a Dalradian basement, but on top of that, we've got huge volcanics, sills, and then a lava succession on the top. And we have a huge ring fault, another big caldera. So again, it's cover on top of the base Dalradian that Alex been talking about so far. But this one and the Ben Nevis are the main expressions of extrusive igneous rocks that we have in the Grampian terrain. We have two minor ones in the northeast. I'll get round to talking about one of them shortly. So next, again, now I'm jumping back. This is the Cairngorms. And I've used this slide to illustrate as much, not just the granite pluton, which Emily is going to talk about after me, but really this is a great illustration of glaciation. We have an enormous amount of glaciated landscape in Scotland, and the Grampian terrain in particular. Here in the Cairngorms, we've got some massive glaciated troughs. This one is Loch Ann. I'm on the slopes of McDoey here, the eastern slopes. This shadow is of the Shelterstone buttress, and massive post-glacial rock falls down into the basin here, including the Shelterstone. We've got all the tors up on Ben Vein. We've got block fields on the summit, which has been a cold ice base. We've got, of course, the trough itself, which is a warm ice base where the ice moved fast to create the troughs over several glacial episodes. But across the terrain, there is endless glaciation features to see. There's a great deal to do with moraines and other periglacial forms as well. It's a whole area to study. This is one of our extrusives in the northeast of Scotland, up in the area called the Cabrach at Ardwell Bridge. There is an exposure of these squashed pillow lavas, and they are lavas. There's evidence of they're porphyritic, and they are also sorry, I've forgotten the word, but there are lots of gas bubbles in them. Excuse me. So this is an interesting area because you can determine the way up of the pillows, which indicate a younging. In this case, more to the northwest, but the overall sequence there is to younging to the southeast of the whole Dalradian sequence. But there's intensive folding, so there are many upside down rocks in this particular area. So it's a great area to go to discuss and an exercise to consider ways up or not. Jumping now to the Banffshire coast, the old Banffshire coast as we knew it. This is Port Soy. Now, Alex hasn't yet mentioned the gabbro intrusions that we have around the northeast, particular to the northeast of Scotland. But one of them outcrops at Port Soy and is really there. There's a whole tectonic mélange associated with the gabbro and its shear zones. And also the surrounding Dalradian rocks are very much affected by tectonic stresses. So here in the foreground, we have a very striking light-colored anorthosite, a component of basic intrusions, almost pure anorthosite, feldspar. And in the background, we actually have mullioned quartzite, Dalradian quartzite, which again shows the stresses in the area. So Portsoy is a fantastic area to visit. The whole northeast, or the coast, the south coast of the Murray Firth in this area is actually a very good cross section of the Dalradian, which is very steeply dipping to the southeast throughout much of its exposure or much of its occurrence in Aberdeenshire. So you can actually walk through a great cross section of the Dalradian from the Grampian basement, or Grampian, not Grampian, lower Dalradian, right through to the turbidites that he was just starting to talk about of the Southern Highland group. In the middle, you've got this disturbance at Portsoy caused by the gabbro, but also we have a Portsoy lineament locally as well. So there's a lot going on there. Coming inland, same intrusion. Again, a big gabbro intrusion running through central Aberdeenshire. In this case, we're in Glen Bucket, which is a tributary glen of the River Don. Within the gabbro, there are some very pegmatitic sections where you have all this conspicuous black mineralization. And if you look carefully at the black minerals, you will find they have a 90-degree cleavage, so they are pyroxenes. This particular specimen comes from a dioritic margin of the gabbro. And again, looking carefully, probably not visible on this slide, but you can pick out 120-degree cleavages, which indicates it's an amphibole or hornblende. And just to confuse matters further, there are several granitic enclaves within the intrusion, and they have quite a good incidence of black schorl tourmaline. And again, all three rocks look very similar, but you can actually distinguish the three different minerals. So the Glen Bucket pegmatite can be any of those three rocks. And quite fun to go and find them. Exposure is very poor, but there's a lot of float around, and you can find good specimens in their areas. Carrying on from that, still in Glen Bucket, within the intrusion, the gabbro intrusion, we have several very large xenoliths of the local country rock, in this case locally called the Craigie Var Formation, which is part of the Argyll group. And some seams are very rich in garnet, and you can just see from the fingernail there, we're talking about centimeter size, quite nice form of garnet. Local lore says that everybody in the glen had some jewelry made out of this garnet at one stage. Another story is that some local 120 years ago or so got some gunpowder and blew half the rock down the hill. You can still see the debris to this day. But there are still lovely garnets to be seen within the rock. Quite nice. They're quite hard to get out, so nobody seems to have bothered, which is rather good. Long may it last. Back down now to Argyll. This is on the shore of Loch Linnhe. This is E.B. Bailey, one of the very famous geological surveyors, called this Tiger Rock. And here we are, we're on the Ardshiel Peninsula, south of Ballachulish. And this is a transition series rock, really between the Ballachulish slate and the quartzite and limestones that occur on the Ardshiel Peninsula. So this is a transition of dolomitized limestone. There's some sammites in there, and it forms this very vivid striped rock. Also to be found in a small quarry just up the hill behind Ballachulish itself, a little limestone quarry there. So as I say, right on the shore of Loch Linnhe. On the same peninsula, lots of buckle folding in evidence, where you can measure it, look at it, and discuss its relevance to the greater folding picture in the area. The Ardshiel Peninsula is a massive syncline, but there are lots of these parasitic folds that give you vergence ideas as to what the structure is. So quite a nice example, a very visible one. Coming back to Deeside, we're near Braemar here, again in Appin series rocks, Ballyhooly subgroup. And here we have multi-phase folding. If you look carefully here, you will see very tight to isoclinal folds here and here as well. And these are the F1 folds. That whole F1 tight sequence has been buckled and folded by F2. And there is in the same area evidence of possible F3, F4 folding, not at this particular locality. So again, a nice excursion from Braemar, who will see these sorts of things. Here we are in Glentilt, one of the famous Heddle localities, not the marble itself, but further up the Tilt River, where he saw schists being intruded by granite. This is the marble, quite close to the gamekeeper's lodge, and it's nicely cleaned, I guess, several times a year by the flooding river. So it's not a well-known one. There's some nice carved pieces in Blair Castle just downstream, showing it off to its best. There's lots of loose fragments kicking about as well, so you don't need to hammer the main exposures. Now, the main lecture hasn't got to this yet, but we have quite a lot of Devonian Old Red Sandstone cover within the area. Mostly, well, towards Inverness, it's more continuous, Murray continuous, but round about the Aberdeenshire area, it's mostly in large faulted, down faulted sections on the shore. So a couple of them here, it's pretty extensive, pretty thick sequences. This is one at Gameray or Gardenston on the Banffshire coast, showing a lot of conglomerate there. If you go next door to Pennon, a few miles along the coast, similarly, but here we've actually got the unconformity between lower and middle Old Red Sandstone. So quite a lot to see, a lot of sedimentology to be done in these locations. Very dramatic locations, mostly all Dalradian cliffs, but with these faulted enclaves of sediment. Again, staying with the Old Red Sandstone, these are well-known pillars on the River Spey, a dramatic situation, and you can go and see these and stay out of the way of the fishermen looking for salmon. But quite dramatic pillars, very soft conglomeratic rock. The Spey at this point, in fact, for most of its length, follows major faults. Particularly further up, it follows sorry, I forget the name here. No, it's escaped me. One of the major northeast southwest trending faults in Scotland comes right down Spey side, and the Spey follows it. Here, there's a branch fault goes across to the coast, possibly a splay fault at the end of the Erich Leyden fault. That's the one I'm trying to remember. And again, excuse the black and white picture, I couldn't find my color original, but this is one of the big outliers, and there are several outliers within the area. This is the Ailnat Gorge just south of Tomintoul, where there is a considerable thickness of Old Red Sandstone, at least 100 meters more in places. Very faulted, so difficult to judge the total thickness. And within the gorge, which is a giant meltwater channel from glaciation, in the Cairngorm area, flowing east, exposes the thickness of this conglomerate, but also the boundary, lying on top of the Dalradian base, is visible in certain parts of the gorge. Quite a difficult place to get into, but very worthwhile once you're in there. Very, very impressive place, and reminds us just of the sheer amount of sediment coming off the Caledonian mountains. And not all on the coast. This is another faulted basin which has accumulated quite a lot of sediment. Coming younger again, quite a well-known picture to many of you, I'm sure. We're now in the Permo-Triassic of Murray, and on the Murray coast, we have several faults running parallel with the Firth, and the Murray Firth is a rift basin. And this is one of the major on-land faults that's very, very evident, running, as I say, east-west. not on the coast. This is in Clasher Cove, or we used to know it as Primrose Bay when I was a boy in Elgin. Very dramatic fault, and you can in fact inspect all sorts of features of the fault. And Aberdeen University have some nice flyby material on this fault. You can examine it in close detail. Dr. Claire Bond there has done a number of these things. So something quite different again, in the same locality at the Clasher Quarry. And the Clasher Quarry is well known for sandstones appearing even in recent buildings. For example, the extension of the National Museum of Scotland in Edinburgh uses the Clasher stone, a very attractive stone. But at the quarry, some years ago, a lot of these footprints were extracted and put on display above the quarry in a public place. Sadly, they've been allowed to deteriorate quite a bit, but Dave Longstaff of Elgin, a volunteer at Elgin Museum, is currently cleaning and refurbishing the area to make them visible again. These are all reptilian footprints, not dinosaurs, but reptilian, but very, very impressive nevertheless. Several different types of footprint there, and that's at the Clasher Quarry. Also, in the same area on the beach, there was for a while a millstone industry. Not much known about it, but across the wave cut platform in the Hopeman area, Hopeman and Cowsey area, you will find millstones lying. I believe there are 6 or 7 of them in various states. This is one that's easily found near the Hopeman end. So an interesting bit of history there that appears. And lastly, I'm just going to say something about the Quaternary geology. This is in the Findhorn Valley, where there's all sorts of came terraces and alluvial fans, and just about any type of formation, glacial, post-glacial, periglacial, that you might imagine. And this was a little expedition with the Highland Geological Society with John Merritt of BGS. Very, very interesting and quite new to me, not my area of expertise, but there's a lot in the Quaternary that can be shown to be of great interest. And lastly, finishing up more Quaternary, this is one of the very famous localities in the Grampian terrain, Glenroy, the parallel roads. Here, the margins of ancient lake floors, 3 different levels across here. But also in this picture, a massive underwater alluvial fan, again with several complications of levels. Again, I'm not an expert on this, but there's a lot of research currently still going on in this area. Very, very vivid, very, very conspicuous. And just a reminder that it's not all about rocks. There is a great deal of interest in glaciology and in Quaternary formations generally. So that's a very rapid set of tasters. Apologies again if there are things that are obviously missing, and there are, but it was just intended to add some color and interest to the presentations. I'm obviously happy to take any questions later on.
So, hi everybody, hopefully you can see my screen, and thank you very much for sticking with us. Just move that. So yeah, Alex has just given us a good summary of the Caledonian granite, so I'm going to continue that and talk to you about the Cairngorm granite in particular. So here we've got some fantastic images that I've pinched off the internet of the Cairngorm National Park. And the Cairngorm granite is actually responsible for the rugged landscape of the national park. It's incredibly hard and resistant to weathering, and it actually now forms 5 of the highest mountains in the UK. But since the 1700s, people have been interested in this granite, not just because of the beautiful landscapes that it produces, but also because of the gemstones that it produces. So, oh, if my slides actually work. Why are you not going forward? There we go, sorry. So just a quick flash of this graph map again from last week, just to show you where we are. Another big red blob of granite. And as I said, in the middle of the Cairngorms National Park, which is one of only 2 national parks in Scotland. So here we have a chunk of the Cairngorm granite. It's a Caledonian granite, so it's 408 million years old, and it's the ultimate source of the gemstones I'm about to talk about. So Alex did mention briefly how granites form, so just a quick recap. These are bodies of molten rock that are trapped underground. And because they're trapped underground, they're quite insulated, so they cool down slowly, and that gives a chance for these crystals to grow quite big. So you can actually see these crystals in the rock. In granite, minerals like quartz and feldspar and micas crystallize out of the melt first. And that means that as the body crystallizes, the remaining melt is continually enriched in elements that don't like to be in these minerals. So these are elements like beryllium and lithium, phosphorus, fluorine, and water. So when these elements are concentrated, that lowers the crystallization or the solidification temperature of the melt, and it also reduces the crystal nucleation rate. So this means that fewer crystals are forming, and the ones that do form have the chance to grow quite large and in a nice crystal shape because they're not competing with other crystals. And that leads to the formation of a rock called pegmatite. And this is pegmatite here. As you can see, it looks quite similar to the granite, and that's because broadly it has the same composition. But if I turn this specimen round, you can see that we have some lovely big crystals here. And we also have some more interesting crystals forming. So these are crystals of minerals that are incorporating these incompatible elements, and these are the gemstones. Pegmatites are great sources of gemstones globally. The crystal size here in this one is only a couple of centimeters, and in the cairngorms in general, I think the biggest have been 10 to 20 centimeter big crystals. But globally, the largest crystal from a pegmatite has been an 18-meter long beryl crystal from Madagascar, which is just incomprehensibly huge. So I'm going to talk about some of these gemstones now. So in the cairngorms, the three minerals that we consider gemstones are topaz, beryl, and quartz. I'm going to start off with topaz. So these are all going to be specimens from the National Museum Scotland collection because I want to show them off a little bit. So these are the more crystalline specimens that we have in the collection. But normally you find topaz crystals from the cairngorms like this, kind of tumbled, water-worn pebbles. So these have been naturally weathered out of the rock that they formed in and then transported in rivers, bashed about a bit, and you end up with this kind of frosted exterior. So they don't really look like much. But if you break them open or if you polish some of the surfaces, as you can see on the left here, they're beautifully clean, translucent, pale blue crystals. So pure topaz is colorless, but the color comes from either incorporating trace elements into the crystal, so then you get like pinks and browns and yellows, or from defects in the crystal lattice, which is how you get blues. So these crystals have been irradiated over millions of years by the granite that they were hosted in, and that gives it this lovely pale blue color. Unfortunately, the pale blue topazes aren't that valuable. Most people want a stronger blue color. So these kind of pale blue topazes are normally further irradiated or heat treated to intensify the blue color. As topazes are so rare, I didn't think I said this, but topaz is the rarest of the three gemstones in the cairngorms. We don't actually have any faceted topaz to show you. So I'm going to hop on to beryl. The beryl is the second most common stone found in the cairngorms, gemstone, sorry. And you might recognize the word beryl maybe as it's the mineralogical name of the gemstone emerald. Sadly, we don't actually find emeralds in the cairngorms. None of them are that intense green color. Instead, we find colorless to pale blue to pale green beryls. So the gem quality beryls from the cairngorms are aquamarines rather than emeralds. So here we have two rough pieces of emerald, so that rough being the mineral before it's cut into a gemstone. And on the left here, sorry, you can see that beryl forms these lovely hexagonal crystals with flat terminations on the ends. This is what they naturally look like. So these two aren't gem quality, they're too opaque, but these ones are approaching gem quality material. They're probably a little bit too included, but they're nice and glassy, translucent with a nice color. This pale green isn't particularly valuable as a color. People want the intense green of an emerald, but still they're approaching gem quality. Interesting thing about these crystals here is that they don't have nice crystal faces. They look a bit unhappy, and we call these etched crystals. So this occurs because as the melt evolves, so the fluid that these minerals are crystallizing out of, it crystallizes different minerals at different times, and the composition evolves. So the beryls would have crystallized out first, and then as the melt evolves, you end up crystallizing out things like topaz. But by the time you're crystallizing out topaz, the fluid has become incredibly acidic. You need like hydrofluoric acid in the system to crystallize out topaz. And at that point, it's eating away at the earlier formed beryls. So that's what's happened here. And here we have some lovely cut beryls that we have in our collection. The blue ones here are considered aquamarine, so this is lovely sea blue. And then at the bottom here, we have a colorless one. Interested, a bit of a bad color on the picture there, but trust me, it's colorless. And that's what we call that goshenite. And then finally, we're on to quartz. So you're all probably familiar with quartz in some way. It's actually the second most abundant mineral in the Earth's crust after feldspar, and it grows into these recognizable pointed prisms. So quartz can be a range of colors, and we give it different names depending on its color. So purple quartz we call amethyst, yellow quartz we call citrine, colorless quartz rock crystal, and this kind of dark brown gray quartz we call smoky quartz. And smoky quartz from the Cairngorms is quite famous. It's known just as simply Cairngorm quartz or Cairngorm stone. And yeah, this kind of, when you find it in the rough, it's this black color. It's not truly black. When you polish some surfaces and put a light behind it, like we've done on the specimen on the left here, it is this deep kind of brown or gray color. And the color of this quartz, again, is through irradiation from the granite. So you have aluminium in the crystal structure, along with other trace metals, and then the irradiation makes the color. So in the bottom right here, we have a slice through one of these crystals. And you can see that the color isn't distributed evenly. You have zoning in a lot of these crystals. And in other crystals, you have multiple generations of crystal growth, like the one on the left. So this has a nice phantom quartz crystal inside it. So that was an original quartz crystal, and then more quartz has grown around it. So actually finding gem quality, translucent, inclusion-free, nicely colored material is relatively rare, but people obviously have found it. And here we have a selection of different colors of cut Cairngorm quartz, just to show you a bit of a range of the variety of colors. So we've got kind of very pale gray to orange to the brown. And skilled jewelers will sometimes try and make a feature of the variety, like the different colors or the zoning in the quartz. So the bottom left, again, it's not the best picture to show it, but this is actually a party colored stone. So half of it is brown and half of it is colorless. But this is not as sought after as the nice colored stones. And also sometimes the color isn't what the jeweler would like it to be. So again, these stones are kind of treated to get the color right. So either they're further irradiated or heat treated to manipulate the color. And this has been a common practice right the way back to the 1800s. So today it should be disclosed if your stone is treated. And yeah, Cairngorm stones have been said by some to be the national gemstone of Scotland, though I'm not sure how official that is. And this is likely due to the tradition of including these stones in jewellery associated with Highland dress. So these are a couple of examples we have in our systems collection. And during the 1800s, there was a big boom in the demand for Scottish jewellery like this. So ones including Cairngorm stones and also other pebble jewellery that includes things like agates. And it was due to a variety of factors, including increased trade from railways and the romanticisation of the Highlands, and also a bit by Queen Victoria, who it was reported that Cairngorms were her favourite mineral and that she collected Cairngorms on her trips to Balmoral. And this meant that hunting for these stones became increasingly profitable, and in some cases more profitable than farming. So many people turned to crystal hunting as their primary income. And that does mean, sadly, that to find examples like this in the Cairngorms in modern day is incredibly rare, and you'd be very lucky to find good gem quality material nowadays. But it's still worth a hunt, and people do. So those were the gemstones of the Cairngorms, and there have been about 30 different minerals found in the region. So just right at the end, I wanted to cram in some other minerals because it's an excuse too. So this is fluorite, so it's my favorite mineral. I couldn't not include this one. So we've got some nice purple and green fluorite in the same specimen. And then we've got phenakite. This is a mineral that has commonly been confused for topaz and also has a history of being sold as cairngorm quartz to kind of bump up its value. But it's actually most chemically similar to beryl. And then to close us out, we have some graphic granite. So this is quartz and feldspar growing together, and it's commonly found as a transitional phase between the granite and the pegmatite. So that's me. Thank you very much for listening. If you want to know more, then please check out the book Crystal Mountains by Roy Starkey. So that covers all of what I've said today and more. And it's a really good book, and I do recommend it. And then there's a paper about pegmatites if you're interested. So thank you very much.
Awesome. Thank you so much, Emily.